This is a plot of the temperature that an interferometer would be sensing at the top of the standard atmosphere. This is computed using a radiative transfer model. So the x-axis here is the wavelength from about 4 to 15 microns, and the y-axis is the brightness temperature, so it's hot at the bottom and cold aloft. Standard atmosphere has a surface temperature around, say, 288, 290 Kelvin, and you'll notice that at some wavelengths you are seeing all the way down to the surface, but there are some other regions where, because of absorption by gases, different kinds of gases, you have cooler temperatures. For example, in this well-known water vapor absorption region, energy that's being emitted by the surface is all emitted radiation at 6.5 microns, is absorbed by water vapor and then re-emitted from a higher, colder surface, and that continues up through the atmosphere until you get to the top where there isn't any water vapor above you, and then the emitted radiation can escape to space and be sensed by the satellite. But by that time, the emitting region is very cold. So let me take off these gases and ask you, if you wanted to sense particular things in the atmosphere, where would you put your channels or your bands on the satellite? And of course, if you want to see the ozone, you're going to put it in this ozone spike here. You might want to detect SO2. You want to detect water vapor in the atmosphere, but you're also going to be interested in seeing what's going on near the surface, so you'll have channels there. And if we look at where the ABI channels have been spaced, hopefully that makes a little bit more sense. Now, because this red line here is computed from a hypothetical atmosphere, we can remove gases. So here's again, the Earth-emitted infrared spectra, but here's what it looks like if you don't have water vapor in that atmosphere. So we'll just toggle between the two of these. And because we have these two spectra, we can take the difference. And we can see, okay, what is the difference in temperature that's due to water vapor? And that's shown here. So the temperature at 6.5, 6.9, and 7.3 is much colder in this standard atmosphere because of the absorption by water vapor. Here's the 10.3 micron. And you'll notice its temperature is very close to what the atmosphere is without water vapor. It's maybe 1 or 2 Kelvin colder. And as you get, so that's the clean window. And as you go to the window channel at 11.2 and the dirty window channel at 12.3, you'll notice that this difference value is getting larger and larger. So when you have more and more water vapor absorption, the brightness temperature you're going to be sensing is going to be a little bit cooler, and is going to be cooler and cooler. This is for water vapor. So we can do the same thing with other gases. So here's the IR spectra again, and here we have it with no ozone. And as expected, there's a big signal around 9.6 microns. So we'll see here. So here we have the ABI spectra, and here we have the difference plot that's due to ozone absorption. And there's a big signal at 9.6 microns. If you really wanted to detect ozone everywhere, you'd also have a channel maybe at 4.7 microns and maybe one out at 14 microns. But on ABI, we just have the 9.6 micron channel. So here we have the same difference field with CO2. So if we're looking at the absorption due to CO2, and we look at the difference field there, you'll notice the big signal is at 13.3 microns. So this is the CO2 channel. It's right on the shoulder of this absorption band. But there's also a lot of stuff going on, say, in the 3.7 up to 4.7 region. And you might recall that if you look at the GOES sounder, there are a lot of channels in this region because it's looking at the temperature in the atmosphere and in the stratosphere. That's when you have a positive value here. That's also out here. So the GOES sounder was able to do some temperature sounding in the stratosphere because of the channels in this region around 4.3 microns, and then also up around 15 microns. But for the ABI, most of the CO2 absorption is in the 13.3. You do see a little of it in the 10.3 and in the 9.6 as well. Now, is this emitted or reflected radiation? So this is the Planck function for the Sun and the Earth next to each other, and you do see that there's an overlap around 3.9 microns. So 3.9 microns is that unique channel that has both reflected solar radiation and emitted terrestrial radiation. Typically there's a lot more reflected solar radiation when the sun's up, And all the other channels, you'll notice that the terrestrial radiation just completely swamps the reflected solar radiation. So when we're looking at these when we're looking at this kind of wavelength range, only down here will you have any kind of solar radiation, reflected solar radiation. You can call it contamination. For the other regions, you're not going to have any solar reflectance. And reflectance is, of course, very important in the visible and in the near infrared, the 0.86 to the 2.2 micron channels.